Hello, I'm going to talk about statistical mechanics. Let me start with a simple system that has n particles and just two energy levels, E1 and E2. The idea is to eventually be able to calculate the heat capacity of this system. And to calculate the heat capacity, we must first find the total energy. Because from the total energy, the rate of change with respect to temperature is just the heat capacity. And starting from the energy levels, we can find the total energy if we know the number of particles in each level, because the total energy is just the number of particles times the energy level. So how do we find the number of particles N1 and N2? In statistical mechanics, we start with a very simple assumption. We just assume that each particle is equally likely to be in either level. Now that is a very big assumption. There's no reason to believe that, but let's see where this gets us. Eventually we will have to modify the ideas and make it agree with experiments. So starting from the idea that each particle is equally likely to be in each level. So N1, for example, can be 0, so that means that all the particles are on top, or you can have some here and some there. So what we need now is to find the number of ways in which we can arrange the particles in each level. Let me call this omega. Now, omega just is a number to represent the total number of arrangements that is possible for a particular N1 and N2. And the formula is given by the total number of particles N, big N, divided by N1 and N2. Alright. Now this number also gives us an idea of the probability of how likely it is to have N1 particles there and N2 particles there. Now let's look at this idea of the probability further. Now suppose that I plot a graph of this number of arrangements against, say, the number of particles in N1. So what I want to do is, I want to look at different values of N1 and see how this number of arrangement changes. Now if I do that, if I actually put in some numbers and plot a graph, what you would find is a graph that looks like this. Now this graph peaks at the center, at the value here. Let's say that is big N. So it peaks at the middle, N over 2. What this means is that N over 2 here is really the average number of particles we can expect. And the peak here just means that that is the most likely number. And that makes sense because since we are saying that each particle is equally likely to be in either level, you would expect that on average, the number of particles at each level is just half of the total number. So that makes sense. Now what is interesting here is this. From this assumption, alright, you can see that we have really all the possible values of N1 from 0 to what N is possible. So that doesn't really help, because we need n1 and n2. We need specific values of n1 and n2 to find the u. So if all the numbers are possible, then I really don't know what the value of u is. Right? I really don't know what n1 is, and I can't find the total energy. So we're stuck. Now, that's where the next idea comes in. It is that the idea that we are going to be dealing with a huge number of particles. We are talking about atoms in a solid or liquid or a gas. Macroscopic numbers. So it's going to be a huge number, and what happens with this graph is that if n is very large, the graph would actually look more like this. In other words, as the number of particles gets bigger, the graph gets narrower. So this is actually something that you can check by trying out some numbers and plotting some graphs. Now, as it turns out, when n becomes extremely large, right, like the number of atoms in a solid, this peak becomes extremely narrow. So narrow, in fact, that most of the possible values of, say, n1 is just around the center, around n over 2. Now, what this means is that we no longer have to worry about the fact that n1 can have a very large range of possible values, because since the peak is so narrow, it's actually quite unlikely, in fact very unlikely, for n1 to have values which are away from the average value. And this means that we can now confidently say that n1 is just the average value. Alright, it's just n over 2, and likewise for the n2. So since we can be confident of that n1 is a particular value, n over 2, we can then find the total energy. So what we see here are the main ideas of statistical mechanics, which is that we think about the number of arrangements, alright, and we are mainly interested in the case where the number of particles is very large, so that we really only need to be concerned about the average values, the average number of particles, because it's very unlikely for the number to deviate very much from the average. Okay, right. Now, moving on, this particular system, while we're here, let's define some terms. Right. Now, I've talked about two basic ideas here, and one is the n1, n2, the idea of the number of particles at each level. Now, that combination of numbers, n1 and n2, is called a macrostate. Alright, there could be different ways to describe this. I can just think of a macrostate as the number of particles in each level, or I can describe it by saying that it is a distribution of the particles among the levels. So that's a macrostate. Now, and we have already seen that for each macrostate, that means for each possible value of n1 and n2, there can be different arrangements of the particles among these levels. I can exchange the particles in different ways, rearrange the particles, and the number of arrangements for particular n1 and n2 is given by that formula here. So there can be different arrangements, and these arrangements, each of this possible arrangement is called a microstate. So these are the two more abstract terms that we would see in statistical mechanics. Now, having started with this basic idea, let's go a step further. Now, in real situation, there are what we call constraints. There are other factors that comes in and affect the distribution of the particles. For example, there is the total energy. If I have a solid, for example, it can't just take any energy, alright, it will have a certain amount of thermal energy. So let's think about a solid in which the total number of energy, the total amount of thermal energy is fixed. We can imagine such a solid by thinking of something that is thermally insulated. No heat can go in or get out, so that the total number of the total energy is fixed. Now we think of this as a kind of a constraint, a restriction on the system. Now we have already seen one constraint here, which is n, the total number of particles. So in fact, we have really, in looking at this, assumed that the total number of particles is fixed. Alright, which is kind of obvious for normal or ordinary solids. So now what we are going to do is we are going to add in one more constraint, which is that the energy is fixed. So what we want to now do is to learn how to find n1 and n2, this number of particles, in a system where we have these two constraints. Right, so we have n1 plus n2, that's one constraint, and we have u, which is n1 e1 plus n2 e2. So you assume that these two quantities are fixed for this next example, and now I'm going to generalize this further. I'm going to add a plus dot dot dot, which means that there can be more than two energy levels. So what we will try to do now is to find the populations n1, n2 at each level. Now we have seen from the previous discussion that we need to look at the number of arrangements. So this is given by the formula n factorial over n1 factorial, n2 factorial, and so on if we have more than two levels. And we want to look at the number of arrangements which is highest. We want to find the n1, n2 that give the largest number of arrangements, because that's the most likely one. Alright? And for large number of particles, the most likely arrangement would also be the only possible arrangements. Now, in order to find the largest possible arrangement, where we have constraints like this, there is a mathematical method called the Lagrange multiplier, and that's what we are going to use. Now, before that, let me write down a formula that is going to be useful. It's called the Stirling's approximation. Now, the Stirling's approximation looks like this. It says that the log of factorial of n is approximately equal to n times log of n minus n. Now the reason why we're going to need this approximation is this. If we look at the formula for the arrangement. This is a formula with lots of factorials in it. Now, in the idea here is that we are going to try to find the maximum possible value of omega by varying the n1, n2, and so on. We are going to try to do it using calculus. We are going to think about differentiating omega with respect to n1, n2, and so on. Now, but the trouble is, factorials are complicated to differentiate. And since we are going to have to expect a very large number of particles, we can use Stirling's approximation, which actually simplifies the factorial. As you can see, log of the n factorial is approximately equal to this, which has no more factorial. So that simplifies things. So that means that in order to differentiate omega to find the maximum, we are going to, instead of differentiating omega directly, we are going to look at the log of omega and find the maximum for the log of omega instead. Right, let's press ahead. So what we want is to find the maximum for the log of omega. We want to find values of n1, n2 that makes this a maximum, with the condition that they must obey these two constraints. Now there is, the method, as I said, is to use Lagrange multipliers, and in the Lagrange multiplier method, we should not differentiate log omega directly. We should not differentiate the function directly. There is one thing we must do before that. What we must do is, we must somehow bring in the two constraints. And the way to do it is this. For each constraint, let's say for the n, I must first multiply by an unknown constant. Now I call that lambda 1. And for the other constraint u, I must multiply by another unknown constant, lambda 2. Okay, and then I must add these all up. And let me call this L. And then I should maximize the L. In other words, if I want to find the maximum of log omega as a function of n1, n2, I should not differentiate log omega itself and equate that to 0 and try to solve for n1, n2. I should include the constraints for n and u in this way. So I've actually also added in two unknowns. Now these unknowns are called Lagrange multipliers, hence the name of the method. And eventually I have to also solve for lambda 1 and lambda 2. So lambda 1 and lambda 2 become part of the set of variables. So now I have a function in which the variables are n1, n2, dot dot dot, as well as lambda 1 and lambda 2. So to find the maximum, I must differentiate with respect to each of these variables one by one, set the derivative to 0, and then solve for n1, n2, lambda 1, lambda 2. So that's the plan. So how are you going to differentiate this? The first step is to apply Stirling's approximation. We need to apply Stirling's approximation to simplify omega. Let's do that. So let's look at log of omega. Log of omega is log of n factorial minus log of n1 factorial minus log of n2 factorial dot dot dot. And then let's apply Stirling's approximation to each of this. So that will be n log n minus n, bracket around it. Log n1 factorial becomes bracket n1 log n1 minus n1 dot dot dot, and so on. Right, so this is what it looks like. So while we are here, let's find the derivative of log omega as well. So d by dn1 of log omega. Now n1, big N here is a constant, so that becomes 0 when I differentiate. Let's differentiate that. So I have a minus here. Now, oh, that should be n1 down here. Right, so if I differentiate that, starting from the n1 here, I get log n1. Then if I differentiate log of n1, I get 1 over n1 times n1 gives a 1. Differentiate n1 gives a 1. Minus. Now, nothing else to minus because the next terms here involve n2. So since I am differentiating with respect to n1, all the other terms become 0. And this is what I have now. I keep missing out the n. There's a log of n1. Right. So this is what I have, and it's quite simple now. 1 minus 1 is 0, so I have minus log n1. So that's what I get, just minus log n1. Alright, so let's remember this, and let us then look at the Lagrange function and see what the overall derivative looks like. So the Lagrange function is the log of omega plus lambda 1 n plus lambda 2 u, and that is n, big N here is really n1 plus n2 plus dot dot dot, and u there is really n1 epsilon 1 plus dot dot dot. Now if I differentiate L with respect to n1, I should be using partial derivatives, right? Del L by del n1. Now we have already seen just now that after you apply Stirling's approximation to log omega, I get minus of log n1, right? Now if I differentiate that, differentiate n1 by n1 is just 1. Differentiate n2 by n1 is 0 because n2 is a different variable. So I'm left with just lambda 1. And likewise, when I differentiate that, n1 becomes 1 and I'm left with lambda 2 epsilon 1. And all the rest are 0 because all the rest are n2, n3. They are independent of n1. And this is what I have. So since we want to maximize, we want to find the maximum for this Lagrange function, we should set the derivative to 0. And now we can solve for n1. If you rearrange this, lambda 1 plus lambda 2 epsilon 1. Move the log minus log n1 over to the other side. We will find that n1 is equal to the exponential of lambda 1 plus lambda 2 epsilon 1. And you can imagine that you can repeat this for n2 and you get a similar expression, but with n2 and epsilon 2 instead. So if you repeat this for all the n's, you will end up with a list of formula for the n's, and that will be the solution for n1 and n2 and so on. But we still have a problem because we still don't know what lambda 1 and lambda 2 are. And this is what we have to look at next. How do we find lambda 1 and lambda 2? Now in principle, we can combine this with the equations for the constraints and solve for lambda 1 and lambda 2. So let's see where this can take us. So let's take stock of what we have now. We have n1 in terms of lambda 1, lambda 2 and epsilon 1. Likewise, we have similar expressions for n2 and n3 and so on. Now we also have the the equations for the constraints. These are n is equal to n1 plus n2 dot dot. Energy U equals to n1 epsilon 1 plus n2 epsilon 2 dot dot dot. So we have all these. Now, so is there enough equation to solve for lambda 1 and lambda 2? Well, let's have a look at how many equations there are. We have these equations for all the n1 and 2s. Now in principle we know n and u. So we have two equations there, and we have a number of equations here. So since we already have all the formulas for the n1 and 2s, we are just left with the two unknowns n1 and 2, and since there are two additional equations here, in principle there are enough equations to solve for n1 and lambda 1 and lambda 2, but as you can see, it will get very complicated if we try to solve for n1 and n2 directly. But it's possible to actually solve for one of them for the lambda 1. So let's do that now. To make this expression easier, the next step is to simplify this thing. Let me separate the exponential function into the two factors. Now we are going to rename this part, the exponential of lambda 1, and call it a. Alright, so that's renamed as a. And we have likewise for all the n2 and n3 and so on. This will be a e to the power of lambda 2 epsilon 2, etc. And we can actually solve for A by substituting all of these into that first equation for number. Now it becomes obvious once we write it out. So let me write out this after substituting. It would be n is equal to a e to the power of lambda 2 epsilon 1 plus a e to the power of lambda 2 epsilon 2 plus dot dot dot. Now you can see that a is a common factor to all of them. So I can factor out the a and solve for it. And this gives me a is equal to the number of particles n divided by just e to the power of lambda 2 epsilon 1 and so on. Those lots. So this gives us the solution for A. So at least we are now left with just one unknown, which is the lambda 2. So this is the tricky bit. Now in order to solve for the lambda 2, we need to bring in something different. Now in principle it can be solved for numerically, but in practice it is very complicated. So what is done in statistical mechanics is to make use of something called the Boltzmann postulate and to make use of ideas from classical thermodynamics on entropy. Now let's start with this idea of Boltzmann postulate. The Boltzmann postulate is the postulate that the entropy S is equal to a constant, which we call Kb, times log of the number of possible arrangements of the particles among the energy levels. So that's Boltzmann's the Boltzmann postulate. Right. And in fact, it connects this microscopic picture about the number of arrangements of the atoms and particles. It connects the microscopic picture to a macroscopic picture, to the entropy, which is what we would describe about big objects, about heat and work of big objects in thermodynamics. So that's Boltzmann's postulate. And we also use the idea from classical thermodynamics that relates entropy to heat. And that is that the change in entropy is equal to the heat change divided by temperature. So that's the formula for entropy. Right. Now with these two, we shall try to solve for the remaining unknown, the lambda 2. Let's see how to do this. In order to do this, let's go back to the Lagrange function. That's L equals to log omega plus lambda 1n plus lambda 2u. Right. So previously we have differentiated L with respect to N1 to maximize it. So let's now write out the let us express this derivative slightly differently. Okay, previously I've written this out and I've set that to 0. So what I'm going to do now is that I'm going to consider a small change in N1. Okay, and this small change in N1 would give a corresponding change in L. I'm just going to make it easier by using D. So imagine a small change in N1, that gives a corresponding change in L. No, right, okay, that's not what I want to do. Let me rephrase myself. Okay, what I want to do here is to consider the system where the N1, N2 have already maximized the Lagrange function. So imagine that we have this N1, N2, this set of values, which already give the maximum value of that, so that any change in, say, N1, alright, would lead to 0 change in L to first order. So what this means is that if I have, say, a small change in N1, the corresponding change in DL should also be 0. So that's the idea when we are at the maximum of L. Right. Now what I want to do now is to imagine what happens if I put in a little bit of heat. That means if I increase du a little bit, if I put in a little bit of heat to U. Now we are just thinking of a simple system in which doesn't expand when it's heated, so no work is involved. So we are putting a little bit of heat into U. I'll get a du, which is just equal to the amount of heat that I put in. So what happens now to the L if I put in this little bit of heat? This is what happens. If I put in a little bit of heat, some of the particles would move up to a higher level. So what happens is that the number of particles N1, N2 and so on, it would change a little bit. But since I'm at the set of N1, N2 where L is the maximum, if any of the N1, N2 change a little bit, L doesn't change to first order, alright, because it's at the maximum. So to the first approximation it doesn't change, so dl remains 0. But what I want to do now is to look at these quantities. So if the N1 or N2 changes a little bit, number of arrangements omega would change a bit. The total number of particles is fixed, so that doesn't change. And the du, the u changes a little bit. Right. I would call that number 2 du. So this is what I would get. I would have an expression that relates the change in entropy or log of the entropy to the heat that is put in. Now if you recall what I mentioned just now about the Boltzmann postulate, which involves log omega and entropy, and the thermodynamic relation, which involves the heat change and entropy, you see we have a connection between the two. So let me write this out again. Just clean this up. Copy this up here. So this is 0 is equal to d log omega plus lambda 2 du. Right, so this is what we have now. And on the side, let me write down Boltzmann postulate, which is S is equal to kb log omega and the thermodynamic relation, which is ds is equal to du over T. Alright, du is the same as the dq. So you can see the obvious connection here and the similarities. The log omega here can be related to entropy, and the du here can also be related to entropy. And we are obviously bringing in temperature here. So let's make the substitutions. Right. If I rearrange this, I'll have, let's see, minus d log omega is equal to lambda 2 du. So here I can bring in the Boltzmann postulate. So log omega would be S over kb. Right, so this would be S over kb, and du here would be TdS. TdS. Right, and we can, if we compare the two sides, ds are common. So we have, if I rearrange, we would find that lambda 2 is equal to minus 1 over kBT. There, we have just found lambda 2. So having done this, we are now ready to write down the final expression for the solution of n1 and n2 and so on that we have set out to find. Right. So let me just recap. What we have found was that n1 is equal to a, then e to the power of lambda exp lambda 2 epsilon 1. So we were here, and I've shown that we can solve for this unknown a by substituting into the expression for the total number of particles. So that was fine. A we can find. It was lambda 2 that was difficult. And we have now shown that using Boltzmann postulate and thermodynamics, we have now shown that lambda 2 is equal to minus 1 over kBT, and we can now plug this into here to give us a exp minus E1 over kBT. And here we have our final expression, and with a temperature coming in as well. And this expression here is called the Boltzmann distribution. We'll stop here.